All right, diving in today, folks. We're going deep into propositional functions.
Really crucial stuff.
Yeah, like, can't understand modern logic without them, right?
Absolutely.
We've got our trusty Stanford Encyclopedia of Philosophy article here.
Oh, yeah, the gold standard.
So, for all you philosophy nerds out there, think of this as like a concentrated shot of propositional function knowledge,
Exactly, getting right to the core of it.
Cutting through the jargon, really grasping what they are, where they came from, and why they still matter.
Their history, their significance, their ongoing relevance in philosophical logic.
All right, so propositional functions, before we even get into the nitty-gritty, why are they so important for a philosopher?
Well, they're fundamental to understanding how we analyze the structure of propositions themselves.
Okay, propositions, the building blocks of reasoning.
Exactly, and how quantification works, all sum, those crucial concepts.
Right.
For a philosopher, grasping the evolution of propositional functions, the different interpretations, that's vital.
Opens up a whole world of logical and linguistic theories.
It really does. We'll be tracing their development, highlighting the key shifts in how they were understood, and emphasizing their impact.
Their lasting significance, especially for philosophy. Okay, so where do we even begin with this story?
Well, before propositional functions as we know them, traditional logic had its own way of dealing with similar ideas.
Right, like before the formalization.
Exactly. It all centered around the concept of terms.
Okay, terms. So like the basic units of meaning in traditional logic.
Precisely. And these terms were understood in two primary ways.
Two ways. Lay it on me.
You had the extensional view, seeing terms as representing classes or sets of objects in the world.
Okay, so like dog refers to the set of all dogs.
Exactly. And then there was the intentional view.
Intentional, focusing on what?
The inherent properties or concepts associated with a term, its internal meaning.
Got it. So two sides of the same coin. Extension, what it refers to. Intention, the concept itself.
A fundamental distinction that would have major consequences later on, especially when we get to Frege.
Okay, I'm sensing a philosophical debate brewing here. Can we make this concrete?
Sure, absolutely. Let's take a classic example. The proposition, dogs are mammals.
Perfect. Everyone knows dogs are mammals. So how do these two views, extensional and intentional, interpret that statement?
All right, from the intentional standpoint, dogs are mammals is true because the very concept of dog, all those essential properties, inherently includes the concept of mammal.
So it's like mammal is baked into the very idea of dog.
Exactly. Thinkers like Leibniz, who emphasized the complete concepts of individuals, were big proponents of this view.
Right, Leibniz, with his idea that all truths about an individual are contained within its concept.
Precisely. And other figures like Lambert, Hamilton, Jevons, McCall, they all leaned towards this intentional approach, stressing the internal meaning of terms.
Okay, I'm getting the intentional picture. What about the extensional take on dogs or mammals?
From an extensional perspective, that statement is true because the set of all individual dogs is a subset of the set of all mammals.
Makes sense. All the actual dogs in the world are part of the bigger group of mammals.
That's the focus here, the actual objects, the sets. Thinkers like Boole, De Morgan, Peirce, Venn, they were key figures in this tradition.
Oh yeah, the pioneers of set theory and symbolic logic.
Exactly. Their emphasis on sets and classes would prove really important for the development of modern model theory.
Okay, so we've got these two ways of looking at even a simple proposition like dogs are mammals. But I bet things get more complicated when you start dealing with more complex terms, right? Like conjunctions, disjunctions, negations.
You bet. It gets really interesting, especially when you see how these two traditions, extensional and intentional, diverged in their interpretations.
Oh, a philosophical clash. Give me the details.
All right, let's take conjunction, the and, connective. In the extensional framework, a conjunctive term like AB, think red and square.
Okay, red and square combining two properties.
That was interpreted as the intersection of two sets.
Intersection, so the things that are both red and D square.
Precisely. But in the intentional world, things often went the other way around. AB would represent the union of properties.
Wait, hold on, union. So having both properties red and square would be like adding them together?
In a sense, yes. Think about it. Having more properties actually narrows down the set of things that have them.
I see. Fewer things are both red and D square than just red or just square.
Exactly. And the same reversal happened with disjunction, the or connective.
Yeah.
Extensionally, A plus B, like red or square.
That would be the union of sets, right? All things red or square.
You got it. But intentionally, A plus B was often treated as the intersection of properties.
Okay, so needing fewer properties actually broadens the extension.
Precisely. More things are either red or square than both red and square.
Wow, this flip-flop between extensional and intentional interpretations is fascinating.
It really highlights the philosophical differences in these approaches.
It's like they're looking at the same logical operations but through completely different lenses.
And that has big consequences for how you interpret logical relationships.
Okay, before we move on, what about negation? Where did that fit into this early picture?
Negation. The concept of negation we use in modern logic, what we call Boolean negation, that comes straight from the extensional tradition.
Boolean negation, named after George Boole, the set theory guy.
The very same. Boole and his followers understood negation as the set theoretic complement.
Complement, meaning everything that's not in the set.
Precisely. So the negation of dog would be the set of everything that isn't a dog.
Makes sense. So all those things that aren't dogs form a set of their own?
Exactly. And this way of understanding negation, grounded in set theory, became a cornerstone of modern logic.
Okay, so traditional logic, with its terms and these competing interpretations, laid some groundwork. But it seems like it ran into some limitations, especially when it came to relations, right?
You're absolutely right. Traditional subject-predicate logic, with its focus on individual terms, struggled to capture the complexities of relations.
Relations like, say, John loves Mary, that kind of thing.
Exactly. That's where Charles Peirce's work comes in.
Peirce, the American pragmatist and semiotician, he was interested in logic, too.
Oh, yeah. Big time. He saw the limitations of traditional logic and took a big step towards a more functional understanding of terms.
So how did he tackle this problem of relations?
He introduced the idea of relatives.
Relatives sounds intriguing.
These were terms that, instead of representing single objects or properties, represented classes of pairs of objects.
Pairs of objects, so like a relationship between two things.
Exactly. And this was still fundamentally an extensional view.
So sticking with that focus on sets and classes.
Right, but now we're talking about classes of pairs to account for the structure of relations.
Okay, so loves would be the class of all pairs where the first loves the second.
Precisely. It was a generalization of the traditional logic apparatus to handle dyadic relations, those involving two things.
Okay, I'm seeing how this moves us closer to functions. And what kind of logical operations could you perform on these relatives?
Well, much like with traditional terms, Peirce defined conjunction, disjunction, and negation for relatives.
So you could combine relations with and, or, and not?
Exactly, operating on these classes of pairs in a set theoretic way. But he also introduced a crucial new operation. Composition.
Composition, combining relations in a special way.
Yeah. The composition of two relations, say F and G, written FG, holds between X and Z if there's some Y such that F holds between X and Y and G holds between Y and Z.
That's a bit abstract. Can you give a concrete example?
Sure. Think about the relation is an ancestor of.
Okay. Is an ancestor of?
That can be understood as the composition of is a parent of with itself.
Ah, I see. If X is a parent of Y and Y is a parent of Z, then X is an ancestor of Z.
Exactly. This is a big step towards capturing the transitivity of relations.
Makes sense. And this idea of composition, combining relations to form new ones, that feels very functional.
It is. Peirce was really pushing the boundaries of traditional logic here. And he also developed this fascinating concept called the rima.
Rima, that rings a bell. Isn't that even closer to our modern notion of a propositional function?
It is, very much so. In his later work, around 1892, Peirce introduced the rima as this incomplete entity.
Incomplete, meaning it needs something more to become a full-fledged proposition.
Exactly. He said it contains a copula, or link, which, when combined with the right number of arguments, yields a complete assertion.
Okay, so it's like a template or a blueprint for a proposition.
Precisely. He even gave this great example, is bought by from for rima.
That's like a sentence with blanks to be filled in.
Exactly. It only becomes a truth-evaluable statement when you fill those blanks with specific objects.
Wow, that's strikingly similar to how we think about functions today, taking inputs and producing an output.
It is, and the philosophical implication here is huge. It's a shift from seeing terms as static entities to recognizing their potential for predication.
Okay, so Pierce moved us closer, but it seems like the formal articulation of propositional functions really took shape with the rise of mathematical logic.
Right. Thinkers like Peano and, of course, Frege were instrumental in formalizing this notion of functions within logic.
Okay, let's start with Peano. He's known for his contributions to mathematical logic, right?
Exactly. Giuseppe Peano, though his work on propositional functions wasn't as fully developed as Frege's, his contributions were immense.
So what were some of his key innovations?
Well, first of all, he introduced the modern notation for propositional connectives. Implication, negation, conjunction, disjunction, biconditional. He gave us the symbols we still use today.
Okay, so the symbols for if dot then, not and, or if and only if.
Precisely. He also introduced propositional constants for truth and falsity, T and F. This standardization of symbols was a major step in formalizing logic.
It's like he provided the symbolic toolbox for working with propositional functions.
Exactly. Now, when it came to variables and quantification, things get even more interesting.
Okay, variables, those placeholders that represent any object, and quantification, like all and some, crucial stuff for logic.
Absolutely. Peano used open formulas extensively in his work.
Open formulas, those are like propositions with variables in them, right?
Precisely. And while he didn't explicitly interpret them as functions in the way Frege did, he used them to develop his theory of quantification.
So the seeds of the functional view were there.
They were. And here's a fascinating detail. His system initially only had a universal quantifier.
Only for all, no there exists.
Right, and it was always attached to a conditional or biconditional. So a universally quantified statement would look like this. For all x, if A holds of x, then B holds of x.
Interesting. So his variables were there, acting as placeholders in these open formulas, but their functional nature wasn't fully spelled out yet.
Exactly. He referred to them as indeterminate objects.
Indeterminate objects kind of leaves their ontological status a bit vague.
It does. But remember, Peano's primary focus was on developing a rigorous symbolic language for mathematics.
Right. He was more concerned with the formal system than delving into the philosophical implications.
Exactly. He provided the tools, but it was Frege who really brought those philosophical implications to the forefront.
Okay, Frege, the big name in the philosophy of language and logic. His work seems to be where propositional functions truly come into their own.
Absolutely. Gottlob Frege completely revolutionized our understanding of sentences and their logical structure.
Okay, how so?
He introduced this crucial distinction between sense, syn, and referent, bedutum.
Sense and referent. Remind me what those are again.
The sense of an expression is its mode of presentation, the way it picks out its referent, which is the object or truth value it refers to.
Right, so the morning star and the evening star both refer to Venus, but they have different senses, different ways of thinking about it.
Exactly. Now, Frege applied this distinction not just to singular terms, but to predicates and even entire sentences.
Okay, so sentences have both a sense and a referent. What's the referent of a sentence?
Its truth value, true or false, but it also expresses a thought, its sense.
So a sentence doesn't just point to a truth value, it also conveys a way of thinking about that truth value.
Precisely. And here's where functions come in.
I'm all ears.
For Frege, singular terms like the morning star refer to objects, as we said, but predicates, like is a planet, refer to concepts.
Concepts, those general notions that apply to things.
Right. And crucially for Frege, concepts are functions.
Functions. So a concept takes an object as input and outputs a truth value.
You got it. The sentence Venus is a planet is analyzed as applying the concept is a planet to the object Venus, yielding the truth value true.
Wow, that's so elegant.
It is. Frege's concepts are the direct precursors to our modern propositional functions, functions that map objects to truth values.
And this idea of them being unsaturated or incomplete that we saw hints of in Pierce is central to Frege's view too, right?
Absolutely. He saw functions as fundamentally incomplete, needing an argument to become saturated and yield a value. Objects, on the other hand, are complete on their own.
It's like those chemical bonds needing to be filled.
Exactly. And here's a key philosophical contribution from Frege. The principle of multiple analyses.
Multiple analyses meaning what?
That a single sentence can often be analyzed in more than one way in terms of function and argument.
Can you give an example?
Sure. Take the sentence, my dog is asleep on the floor.
Okay, my dog is asleep on the floor.
You could analyze that as the concept is asleep on the floor, applied to the object, my dog.
Right, the dog is the thing that's asleep on the floor.
But you could also analyze it as the concept, my dog is asleep on, applied to the object, the floor.
Ah, I see. The floor is the place where my dog is asleep.
Exactly. So the logical form of a sentence, its underlying functional structure, isn't always uniquely determined by its surface grammar.
That's profound. It means there's this deeper level of analysis, and the same sentence can have different logical forms.
Precisely. This has huge implications for how we approach logic and the very idea of meaning.
And did Frege apply this principle of multiple analyses to the sense of sentences too?
It seems likely, though, the details of how multiple analyses at the level of reference relate to multiple analyses at the level of sense are still debated by Frege scholars.
Okay, so there's room for philosophical debate even within Frege's framework.
There always is. Now, before we move on to Russell, there's one more important piece of Frege's puzzle: the extension of concepts.
Extensions, that sounds like it bridges back to the extensional view of terms we talked about earlier.
It does. Frege called the extension of a concept its course of values.
Course of values, what's that?
It's basically determined by the truth value of the concept for every possible object. So for "this a dog," its course of values would be the set of all objects for which that concept yields true.
So the set of all dogs, basically.
Yeah, exactly. These courses of values are explicitly extensional, connecting Frege's function argument framework with set theory.
Okay, so Frege gave us this powerful framework with concepts as functions, but it was Russell who actually coined the term propositional function, right?
That's right. Bertrand Russell, building on Frege but also diverging in some key ways, formally introduced the term in his 1903 book, Principles of Mathematics.
Principles of Mathematics, a landmark work. So how did Russell initially understand propositional functions?
Initially, he saw them as a kind of proposition themselves.
So not just functions that produce propositions, but propositions in their own right.
Right. Specifically, he saw them as expressions containing a variable that become propositions when you give that variable a value.
Like X is a philosopher, that's not a full proposition yet.
Exactly. But when you substitute Socrates for X, you get Socrates as a philosopher, which is a proposition.
Okay, so propositional functions are like open propositions, waiting for a value to be plugged in.
Precisely. And in his early work, Russell had a particular view about the composition of propositions.
Meaning what they're made of, their constituents.
Exactly. He was a realist about propositions, believing they were composed of the very entities they were about.
So Socrates is wise would literally have Socrates and the property of wisdom as parts.
That was the idea. And like Frege, Russell also embraced the principle of multiple analyses.
So different ways of carving up a sentence into function in an argument?
Exactly. Different underlying logical forms for the same sentence.
Okay, so how did Russell, in this early phase, analyze quantifiers like all and some?
Initially, he was influenced by the extensional logicians, seeing all as part of a referring phrase that denoted a class.
So all men are mortal would be about the class of men being included in the class of mortals?
That was the early view. But his thinking on quantification evolved significantly.
How so?
Later, propositional functions took center stage. All dogs bark, for instance, would be understood in terms of the propositional function. X is a dog implies X barks.
With the universal quantifier applying to the variable X within that function.
Precisely. The focus shifted from classes to functions as the primary way of understanding generality.
So Russell's views on propositional functions and quantification were developing and becoming more sophisticated. But then, boom, Russell's paradox.
Oh yeah, that was a bombshell.
A major crisis in the foundations of set theory and logic. And it's intimately tied to propositional functions, right?
Absolutely. It's a paradox that arises when you consider certain kinds of self-referential properties.
Self-referential, meaning properties that refer to themselves.
Exactly. To understand it, we need to take a little detour into set theory and Cantor's theorem.
Okay, set theory, sets of sets, I'm ready.
Cantor's theorem shows that the power set of any set, the set of all its subsets, is always larger than the original set.
So you can never have a one-to-one correspondence between a set and all the collections you can make from its elements.
Right, and this implies a hierarchy of set sizes, an idea that has echoes in the logical realm.
Okay, so how does this connect to the paradox?
Well, think about the property of not being predicable of itself.
Not being predicable of itself.
Let's call this property R. So Rx means X does not have the property X.
Okay, so something has property R if it doesn't have itself as a property.
Exactly. Now, the paradox arises when we ask, does R have property R?
Does R have itself as a property? I can see where this is going.
If R does have property R, then by the definition of R, it doesn't have property R.
A contradiction.
And if R doesn't have property R, then again, by definition, it does have property R.
Another contradiction. So either way, we run into trouble.
It's a logical trap, and this paradox can be formulated in terms of propositional functions.
Meaning, instead of talking about properties, we can talk about functions that map things to truth values.
Precisely. And this paradox shook the foundations of logic and set theory.
It shows that naive set theory, where you can just form any set you want, is inconsistent.
And it has deep philosophical implications about the limits of self-reference.
Okay, so how did Russell try to escape this logical nightmare?
His initial solution was the simple theory of types.
Types, like categories or levels of logical entities.
Exactly. The core idea was to create a hierarchy of types, specifically for propositional functions and the classes they determine.
To prevent the kind of self-application that leads to the paradox.
Precisely. You can have a function applying to itself or to a function of a higher type.
So a kind of logical stratification. How did this hierarchy work?
At the base level, you have individuals, the objects in the world.
Okay, individuals like Socrates, planets, and so on.
Right. Then you have functions that take individuals as arguments and output propositions.
Like X is a philosopher, taking Socrates as input and yielding Socrates is a philosopher.
Exactly. And then you have functions that take those functions as arguments and so on, building up a hierarchy.
So you can't have a function taking itself as an argument, which blocks the self-referential move that causes the paradox.
Right. And this type hierarchy mirrors Cantor's hierarchy of sets.
Ah, so just like you have sets of individuals, sets of individuals, and so on, you have this parallel structure in logic.
Precisely. The type theory reflects the idea that you can't treat a set as an element of itself.
Or, in logical terms, a function can't meaningfully apply to itself if it leads to a contradiction.
Exactly. So the simple theory of types was a major attempt to restore consistency to logic.
But as is often the case in philosophy, Russell didn't stop there, right?
Nope. He later felt that simple type theory wasn't enough.
Why not?
Because it didn't fully address semantic paradoxes, like the liar paradox.
A liar paradox, the classic, this statement is false. Tricky stuff.
Very tricky. The problem with the liar paradox is that it seems to arise not just from self-application of functions,
but from self-reference at the level of propositions themselves.
Precisely. Simple type theory doesn't really stratify propositions.
Because in simple type theory, a proposition is just a proposition regardless of its content.
Right. But the liar sentence seems to refer back to itself in a way that transcends this simple typing.
Okay, so how did Russell attempt to handle this more subtle form of self-reference?
He developed the ramified theory of types.
Ramified, even more complex than the simple theory.
It is. This theory introduces a further level of stratification, the order of propositions and propositional functions.
Order, like a ranking system.
In a way, yes. The idea is that applying a function of a certain order to an argument yields a proposition of a higher order.
So the order goes up as you apply functions.
Exactly. And a function must always have a higher order than any proposition it takes as an argument.
So you can't have this circularity where a proposition refers to itself without violating the order restrictions.
Precisely. The ramified theory aims to block that kind of self-reference that leads to the liar paradox.
Okay, I'm starting to see how this works, but Russell himself never gave a fully precise formulation of this theory, right?
That's right. It was Alonzo Church who later provided a more formal and complete account of ramified type theory.
So even Russell's brilliant mind struggled with the intricacies of the solution.
He was grappling with some of the deepest problems in logic.
And these struggles with paradoxes seem to have influenced his broader philosophical views, too, especially his thoughts on propositions.
Definitely. Around the same time, he actually abandoned the idea of false propositions for a while.
He denied the existence of false propositions. That's a bold move.
It was. From about 1908 to 1918, he held this view that what we think of as a false proposition isn't really a proposition at all.
So the Earth is flat. That wouldn't be a proposition on this sphere.
Not a genuine one, no. It would be more like a complex involving the Earth and the property of being flat, but not a unified entity.
A fascinating ontological shift, seemingly motivated by these logical puzzles.
Exactly. Now, this raises the question of how this denial of false propositions affected his understanding of propositional functions.
Good point. If there are no false propositions, does that change how you see propositional functions?
Some scholars argue that even during this period, Russell's logical work, including Principia Mathematica, can still be interpreted as relying on propositions implicitly.
So maybe he was just being really careful about what he called a proposition.
Perhaps. And one reason the ramified theory of types remained relevant was its connection to substitutional theories of quantification.
Substitutional quantification, what's that?
It's a view where a quantified statement, like for all x, fx, is true if and only if all its instances are true.
So you check if A is true, A is true, and so on for every possible value of x.
Exactly. And the ramified theory could help prevent circularity in such a system, especially when quantifying over predicates.
Okay, so even if he was questioning the existence of propositions, the ideas of propositional functions and type theory were still crucial.
Absolutely. They provided a framework for understanding logical structure and the nature of generality.
So in his later work, especially in Principia, how did Russell ultimately conceive of propositional functions?
Given his tendency towards parsimony, minimizing the number of fundamental entities, he often treated them as partial functions.
Partial functions, meaning they don't always have a value for every input.
Precisely. Like, is a prime number that yields a truth value when applied to a number.
But not when applied to, say, a chair.
Right. So the focus shifted from them being open propositions to being functions with a restricted domain.
And the rejection of false propositions wouldn't necessarily undermine this view.
Exactly. In Principia, Whitehead and Russell describe a propositional function as containing a variable x and expressing a proposition as soon as a value is assigned to x.
So it becomes a proposition once you give the variable a concrete value.
Right. And they emphasize its ambiguity, the fact that it contains a variable of which the value is unassigned.
But if they're hesitant about propositions, calling it an ambiguous proposition seems a bit odd, doesn't it?
It does. And this has led to different interpretations among scholars.
Okay, so different views on what Russell really meant by propositional function.
Exactly. Some, like Gödel and Linsky, propose a constructive interpretation, seeing them as linguistic or mental constructs.
Dependent on our ability to think about them.
Right. Others, like Landini, lean towards a nominalist view.
Nominalism. So propositional functions are just names or symbols, not real entities.
That's the gist of it. And then you have realists like Church and Goldfarb who see them as representing objective features of reality.
So propositional functions as existing out there in the world, independently of us.
Precisely. This reflects deeper debates about the nature of logic itself.
Okay, so even after their formal introduction and use in Principia, their ultimate nature remained a philosophical puzzle.
A puzzle that's still debated today.
And the story doesn't end with Russell, right?
No, it continues. The development of possible world semantics and the integration of set theory into logic provided new perspectives.
Possible worlds, those alternative realities that philosophers love to talk about.
Exactly. In possible world semantics, a proposition is typically understood as a set of possible worlds.
The set of worlds where that proposition is true.
Precisely. And within this framework, the intension of a predicate is often modeled as a function from possible worlds to sets of individuals.
So the intention of is green would tell you, for each possible world, which things are green in that world.
Precisely. Now, these intentions aren't exactly propositional functions in the classic sense.
Because they output sets of individuals, not truth values.
Right. But there's a way to connect them through a process called currying.
Currying sounds like a culinary technique.
It's named after Haskell Curry, a logician.
Okay, a logical curry, not a food curry. What does it do?
It transforms a function that takes multiple arguments into a sequence of functions, each taking one argument.
Okay, breaking down a complex function into simpler ones.
In this context, you can curry a function that takes a world and an individual and outputs a truth value.
So true if the individual is green in that world, false otherwise.
Exactly. You can curry that into a function that takes just an individual as input.
And outputs a proposition, the set of worlds where that individual is green.
Precisely. So through currying, you can bridge the gap between these world index properties and propositional functions.
So currying lets you go from functions about properties in different worlds to functions about individuals and their properties across worlds.
Exactly. And this paved the way for more advanced semantic theories, like Montague semantics.
Montague semantics developed by Richard Montague in the late 1960s.
Right. It aimed to provide a rigorous semantics for natural language using intentional logic, heavily relying on functions similar to propositional functions.
And Montague used lambda abstraction in his system, right?
Yes, lambda abstraction is a crucial tool.
For philosophers of language, it's a familiar concept. Remind me how it works.
It basically lets you define a property or a concept formally within the logical language.
So for a formula with a free variable, like x is tall, You can use lambda abstraction to create a predicate that captures that property.
Exactly. Lambda x is tall would represent the property of being tall.
And this lets you build complex predicates and analyze the structure of meaning in a very precise way.
Precisely. Montague's system also included operators for intension and extension.
Intention, the meaning across possible worlds. Extension, the actual value in this world.
Right. And the groundbreaking aspect was how he used all this to translate natural language into his logical language.
So you could take